All right, welcome back to the deep dive. For those of you keeping pace with the bleeding edge of AI, and let's be honest, if you're here, you probably are. You know how crucial it is to stay on top of the latest research. Today, we're cracking open a particularly interesting paper, VideoChat R1, enhancing spatio-temporal perception via reinforcement fine-tuning.
That's right. This piece of work comes from a strong collaborative effort across several leading institutions: Shanghai AI Laboratory, Nanjing University, Zhejiang University.
Yeah.
Quite a few big names.
A real powerhouse team, yeah.
University of Science and Technology of China, Shanghai Innovation Institute, Shenzhen Institutes of Advanced Technology, and the Chinese Academy of Sciences. And importantly, for folks who want to get hands-on, the code is already up on GitHub.
Oh, nice. Always good to see open code. Where's that?
It's at github.com/awarding OpenGLab VideoChat R1.
Perfect. So let's get into it. What's the core problem these researchers are actually tackling here?
Well, the issue is, while LMs are getting amazing with text and even pretty good with static images,
Right.
When you move to video, things get trickier. These models often struggle with what the authors call spatio-temporal perception and reasoning.
Spatio-temporal. So
Yeah.
basically the where and the when of things happening in the video.
Exactly. Understanding where objects are and when actions occur. It's a real bottleneck for, it's like truly deep video understanding.
Makes sense. Video is inherently dynamic.
And what's fascinating here is their approach. They're really diving deep into reinforcement fine-tuning, or RFT,
RFE, okay.
and combining it with a specific technique called Group Relative Policy Optimization, or GRPO. The goal is to explicitly boost this spatio-temporal grasp in video MLLMs.
Okay, so RFT plus GRPO to tackle the where and when. Got it. So for our listeners needing the quick version, the 1-minute summary, what's the absolute headline here?
The headline is VideoChat R1. It's a video MLM they fine-tuned using this RFT and GRPO combo, specifically focusing on spatio-temporal tasks. And the results are, well, pretty impressive.
How impressive.
State-of-the-art performance in temporal grounding, that's the when, and object tracking, the where. We're talking big jumps. Plus 31.8 on temporal grounding, plus 31.2 on object tracking, compared to a strong baseline like Quinn 2.5 VL7B.
Wow, those are significant gains, over
Yeah.
30 points.
And the kicker, it achieves this without messing up its general chat abilities. It can still answer general questions, and they even saw some emerging hints of better spatio-temporal reasoning.
So it gets specialized without becoming dumb elsewhere. That's crucial.
Absolutely. Plus, it's really data efficient. They didn't need, mountains of data for these task-specific improvements. Relatively limited samples did the trick.
Okay, that's a fantastic snapshot. Data efficient, big gains on key video tasks, keeps general skills. Sounds like a win.
Pretty much.
So let's dig deeper now. What was the motivation? Why go down this reinforcement learning route for video?
Well, the context is the recent success stories with text-based LLMs. Models like OpenAI O1, DeepSeek R1.
Right, those really pushed reasoning abilities using RL.
Exactly. They showed that reinforcement learning with carefully designed rewards can seriously boost complex reasoning in the language domain. So the natural next step is asking,
Can we do the same for multimodal models, specifically for video?
Precisely. The paper notes that a lot of current work is trying to adapt those ideas, particularly GRPO from DeepSeek R1, maybe using rule-based rewards to get better reasoning in MLLMs for visual tasks.
But video is not just a sequence of images, right? It has its own complexities.
Totally. And that's a major challenge, they point out. For video understanding, especially reasoning, we don't really have the same kind of rich, established training and evaluation benchmarks that we have for, say, math problems or coding in the text domain.
Okay. So the testing ground itself is less developed for complex video reasoning.
Yeah, the data landscape isn't quite there yet. While they acknowledge some other concurrent work is exploring GRPO for specific video tasks, they argue there's a lack of deeper analysis into how video reasoning actually works in these models.
So it's not just about hitting metrics, but understanding the underlying mechanisms.
Right. So instead of trying to tackle the whole complex beast of video reasoning head-on right away,
They picked a more focused target.
exactly, they zeroed in on spatio-temporal perception. Their rationale was that this is an area where it's, well, easier to get the necessary training data.
Okay.
And crucially, it's easier to design effective rule-based reward systems compared to the fuzzier concept of general video reasoning.
That makes sense. It's more concrete to reward correctly identifying when something happened or where an object is versus rewarding, say, understanding subtle causality in a scene.
Precisely. It's a more accessible starting point for applying reinforcement learning effectively.
So the core idea crystallizes. Use RFT with GRPO, guided by these specific spatio-temporal rewards to sharpen the model's perception of where and when.
Yep. And then critically examine how improving that fundamental perception affects performance across a wider range of video tasks, including potentially more complex ones.
So take an existing video MLLM, fine-tune its perception using this RFT GRPO approach, and see if that boosts overall video understanding.
That's the plan. And the initial findings, as we mentioned, suggest it works really well.
Let's talk about those findings again. The data efficiency stood out.
Absolutely. That's a key takeaway. RFT is remarkably efficient for these task-specific games. With relatively few examples, they got significant improvements in perception without harming general capabilities.
Which is a big deal compared to standard supervised fine-tuning, SFT, right?
Yep.
Especially with limited data.
Definitely. It significantly outperformed SFT when data was scarce. And this efficiency directly enabled their second big contribution, VideoChat R1 itself.
The model they built using this approach?
Right. They used Multitask RFT Training on several spatio-temporal perception tasks together. This resulted in a model that's state-of-the-art on those perception tasks.
Like temporal grounding and object tracking.
But also holds its own or even improves on general QA benchmarks like VideoME, MVBench, and their own perception test.
So no trade-off. You sharpen the specific skills and the general understanding doesn't suffer, maybe even gets a little better.
Exactly. And perhaps the most intriguing part is that subtle hint of improved reasoning. Training on fundamental perception seemed to provide a foundation for better spatio-temporal reasoning, even though reasoning wasn't the explicit target.
Interesting. Like, learning the alphabet helps you eventually write essays, build the foundation first.
Something like that, yeah.
Okay, we keep mentioning GRPO, Group Relative Policy Optimization. Can you break that down a bit more for us? How does it actually work?
Sure. So GRPO is a flavor of PPO, Proximal Policy Optimization, which is a common RL algorithm. But GRPO has a neat twist.
What's the twist?
It doesn't need a separate critic model. Normally in PPO, you have one part of the network, the actor, deciding actions, and another part, the critic, evaluating how good those actions were. GRPO skips the critic.
Okay, so how does it judge the actions, or in this case, the responses?
It makes the MLLM itself do the judging. For a given input, like a video and a question, the model generates multiple possible responses, like a group of candidates.
Yeah.
Then the MLLM uses its own internal mechanisms to score each of those responses within the group. How good does it think each answer is?
So it's self-evaluating its own potential outputs.
Exactly. Once it has these scores for the group, GRPO normalizes them to get a relative quality for each response. It's not about absolute correctness, but how good one answer is compared to the others the model generated right then.
Got it. A relative comparison within the generated set.
Right. And the training objective then just pushes the model to favor generating responses that consistently score higher in this relative comparison. It learns to prefer its own better outputs.
But fine-tuning like this can sometimes make models go off the rails, right? Forget what they knew before.
Good point. That's a classic RL problem. To prevent that, GRPO includes a KL divergence term in its loss function.
KL divergence. Okay, what does that do?
It basically acts as a leash. It measures how much the model's policy, its way of generating answers, is deviating from the original pre-trained MLLM's policy. If it strays too far, it gets penalized.
Ah, so it keeps the model anchored to its original knowledge base while still allowing it to learn the new task.
Exactly. It helps maintain stability and general capabilities.
Okay, that clarifies GRPO. Now, how did they translate this into actual rewards for video tasks? You mentioned specific spatio-temporal rewards.
Yeah, this is where the task-specific design comes in. They created rewards for 5 common video task types.
Let's go through them. What's the first one?
First is a format reward, R format. This one's pretty simple. It just encourages the model to output things in a specific structure.
Like using certain tags.
Exactly. Maybe they want reasoning inside think tags and the final answer and answer tags. The reward just uses regular expressions to check. Does the output match the format? Yes, gets 0 reward. No, gets a penalty.
Simple but useful for making outputs interpretable, especially the thinking process. What about the core perception tasks? Temporal grounding, object tracking.
For those, they used an IOU reward, RIOU. IOU is intersection over union. a standard metric in vision.
Right, measures overlap.
Exactly. For temporal grounding, it measures the overlap between the predicted time segment and the ground truth time segment. Higher overlap means a better reward.
And for object tracking?
Same idea, but spatial. It measures the overlap between the predicted bounding box around the object and the ground truth box. Again, more overlap, more reward. Direct measure of localization accuracy.
Makes sense. What about classification tasks like multiple choice QA?
For those, they used a straightforward accuracy reward, RAccuracy. If the model's top prediction matches the ground truth answer exactly, reward is 1, otherwise it's 0. Simple binary reward.
Okay. And video captioning, that seems trickier to reward automatically.
It is, you can't just match words. So they did something clever. They used another large language model, Qwen 2.572b, as a judge.
Using an LLM to judge another model's output. Interesting.
Yeah. First, the judge LLM breaks down both the predicted caption and the ground truth caption into key events or pieces of info. Then, it checks if the events in the ground truth are logically entailed or covered by the events in the predicted caption.
Ah, so it's about semantic coverage, not exact wording.
Precisely. The reward, recall, is based on the ratio of ground truth events captured by the prediction. Higher recall gets a better reward.
That's a really smart way to handle a generative task reward, so they combine these different reward types depending on the task.
Exactly. Like for temporal grounding and tracking, the reward ARST combines the format reward, R format, and the IOU reward, RIOU. They mix and match as needed.
Okay, we've got the rewards. What about the training data? You mentioned it was efficient.
Right. They use standard benchmarks, but often just subsets. Charade STA for temporal grounding, got T10K for tracking, next TQA, validation set for QA tasks, Fiber 1K for captioning, and a small VidTab subset for quality assessment.
And the sample sizes were modest.
Yeah, ranging from maybe a few hundred up to around 10,000 for some tasks. Not enormous data sets.
And for VideoChat R1, the main model, they did multitask training.
Correct. They jointly trained on temporal grounding, object tracking, and grounding QA, using just over 18,000 samples total across those tasks.
Based on which foundation model?
Mostly Qwen 2.5 VL7B. The only exception was video captioning, where they used the slightly earlier Qwen 2 VL7B.
Okay, methodology clear. Base model, RFT with GRPO, specific rewards, targeted data sets. How did they evaluate all this?
Comprehensively. They used a whole suite of benchmarks. MVBench, their own perception test, and VideoME for general understanding, focusing on the short subset of VideoME because their training data was mostly shorter clips.
Makes sense. And for the specific tasks?
Charade STA and ActivityNet grounding for temporal grounding, in domain and out of domain. Got T10K for tracking, NextTGQA for QA, and Dream1K and VidTab QA for captioning and quality assessment.
A good spread. And the main quantitative results summarized in Table 1 look strong.
Very strong. VideoChat R1 consistently beat the baseline Qwen model, and also models fine-tuned with standard supervised learning, SFT, on individual tasks. The gains weren't just in perception tasks, but also in general understanding on VideoMe. Really validated the multitask RFT approach.
And what was that interesting point about the thinking prompt? Think tags.
Yeah, that was curious. For the basic perception tasks, grounding, tracking, adding that chain of thought prompt during inference didn't really help consistently. Sometimes it even hurt slightly. But for the more complex tasks like QA and the general VideoME benchmark, explicitly prompting it to think did lead to noticeable accuracy boosts.
So chain of thought seems more beneficial when the task requires more abstract reasoning, less so for direct perception.
That seems to be the implication, yeah. Their interpretation aligns with that.
They also did ablation studies, right? To isolate the effects of different components.
They did. Really useful for understanding what contributes what. Table 2 looked at temporal grounding specifically.
What did that show?
Confirmed GRPO significantly beats the baseline and SFT. Also, importantly, GRPO was more robust to overfitting performance, kept improving with more training epochs, unlike SFT, which might plateau or degrade.
That's a big practical advantage.
For sure. And interestingly, with more training, GRPO even started to outperform some specialized vision expert models on certain metrics. And the thinking prompt did show some benefit here in later training stages.
Okay. What about object tracking in Table 3?
Similar story. Substantial gains for GRPO over the baseline in SFT, reinforcing the method's effectiveness for spatial perception too.
And Table 4, the video QA results.
Showed GRPO works well even with limited data for QA tasks, improving both NextDGQA and VideoME. And here thinking did play a more significant role. They also noted the glue, the temporal grounding cues in grounding QA, helped a lot on complex tasks like video ME.
So providing explicit time references helps the model reason better about the video sequence.
Seems like it. Then Table 5 looked at captioning and quality assessment.
How did GRPO fare there, especially with the Judge LLM reward for captioning?
Even though they admit the captioning reward wasn't perhaps perfectly tuned, GRPO still outperformed SFT significantly on the Dream 1K captioning benchmark and showed gains on VidDebi QA. Suggests GRPO has potential even when rewards are less precise.
And finally, the multitask training aspect in Table 6. How did training on multiple tasks together work out?
Really well. They found a synergistic effect. Training on a mix of spatiotemporal tasks with GRPO often achieved performance close to or even better than training intensely on just one task.
So the tasks help each other.
It suggests they do, yeah. Points towards the potential for even larger scale multitask GRPO training in the future for more general video understanding.
So across the board, GRPO consistently shows advantages over SFT, especially with limited data, and multitask training looks promising.
That's the gist of the ablation results.
They also compared chain of thought output versus direct output more generally.
Yeah, and as we mentioned, for the core perception tasks in this study, chain of thought didn't show clear benefits. They're hypotheses.
Correct.
Maybe the tasks themselves are too direct, or they didn't have enough of the right kind of data to train effective video-based reasoning chains yet.
Right. It's not automatic that a technique from text translates perfectly to video without adaptation.
Exactly. More research needed there on defining suitable video reasoning tasks and how to best elicit and evaluate that reasoning.
And they included qualitative examples, figures 2 and 3. What did those show?
They really help visualize the improvements. You can see VideoChat R1 identifying much more accurate time intervals for events compared to an SFT baseline.
Okay.
And in the QA examples, it not only gets the answer right, but provides pretty good temporal glue, the supporting time periods. It shows a degree of logic, even if it's simpler than, say, complex math reasoning and text models.
So it looks like it's genuinely understanding the where and when better.
The examples definitely support that conclusion.
Okay, bringing this all together then. As we wrap up this deep dive, what's the big takeaway for AI researchers, ML engineers, anyone working on video understanding?
I think the most significant finding is the demonstration that RFT, specifically with GRPO, is a really powerful and data-efficient tool for enhancing targeted capabilities in video MLLMs.
Improving specific skills without breaking everything else.
Precisely. VideoChat R1, achieving state-of-the-art in spatio-temporal perception while maintaining general chatability, all with relatively modest data, is a really strong proof of concept.
And the model itself, VideoChat R1, seems like a valuable contribution.
Absolutely. It sets a new benchmark. And making the code open source is fantastic for the community. It will definitely spur more work in this direction.
What about future directions? What open questions did the paper leave us with?
Well, they highlighted the ongoing need for better video reasoning tasks and evaluation methods. That's still a frontier. And they also pointed to the potential for scaling up this multitask GRPO training. Could we train on even more diverse video tasks simultaneously?
So lots more to explore building on this foundation.
Definitely. It feels like a solid step forward, but also points the way towards much more sophisticated video understanding down the road.
Well, this has been incredibly insightful, a really interesting paper pushing the boundaries of video MLLMs. Thanks for breaking it down.
My pleasure. It's exciting work.
For everyone listening, I really encourage you to check out the paper, VideoChat R1, and the code on GitHub if you're interested, and maybe take a moment to think. How could AI that truly grasps the where and when in videos change things? From autonomous driving to smarter video search to new interaction paradigms, the possibilities are fascinating when AI starts to properly understand dynamic scenes. That's your food for thought. Thanks for tuning into the deep dive.